Our problem today is the instability of a penetrating blade. The blade is an elastic rod of bending stiffness B and total length L bar. The elastic rod slides into a sliding sleeve here, which is perfectly smooth and without any friction. The only axial constraint in this system is this linear elastic spring of stiffness K, which carries all this load P. This is a situation where this elastic rod has buckled, and so we see here a flexural mode. And please note that the free length of the beam is L bar minus L in, where L in is the amount of the elastic rod inserted into the sliding sleeve. This system is interesting from several points of view. It displays several interesting features. The first is that the buckling is governed by the relative spring stiffness versus bending stiffness. And this is easy to see because if this spring is particularly stiff, the system will buckle insisting loading. But if this spring is vanishing stiff, then we will have that the blade will penetrate the sliding sleeve without any buckling. And in particular, there are several features connected to this. And first of all, we observe more than one buckling load associated to each bifurcation mode. Usually there is one buckling load associated to a bifurcation mode, but this is not true for this system. And then we see that a decrease in the buckling load is connected to an increase of stiffness. So if I increase the stiffness of the spring, then the buckling will occur earlier. Also, there is a finite number of buckling loads associated to all possible buckle modes. This is also a special feature because usually continuous systems display infinite number of buckling loads, and the problem is a Sturm-Liouville problem. In this case, it's a modified Sturm-Liouville problem because the number of buckling load is finite. Moreover, another important feature is number 2, is the restabilization of the straight configuration. I mean, initially, this straight configuration is stable. If I insist loading and I have buckling, this configuration becomes unstable. But for certain stiffnesses of the spring and beam, we can observe that after this buckling, the straight configuration returns to be a stable configuration. Finally, the last feature is the presence of an Eshelby-like force associated to the presence of the sliding sleeve and the buckling. So when the structure buckles, there is here an axial force, which is an Eshelby-like force related to the fact that the bending of the system releases energy from the elastic spring. This feature has been explained in detail by Bigoni, Del Corso, Bosi and Miseroni in a submitted paper. And here is essential because this Eshelby-like force completely changes the equilibrium of this system. This is an important point, and to elucidate this point, I have to show you these two configurations. The first on the left is simply mistaken because there is no Eshelby-like force, and so if we ignore this force, vertical equilibrium implies that this dead load is equal to this dead load, and the spring is simply compressed. It means that if I insist loading, the spring will continuously short. But in this situation, we have added the Eshelby-like force, which is an axial force, which is the square of the applied load times the square of the arm of this load, divided 2 times the bending stiffness of the beam. So the force here is different from this force because we have here the Eshelby-like force. And this force changes completely the equilibrium here. And in particular, the spring carries less load than in this case. And in particular, if we do an experiment with this configuration, we will see that this edge of the structure will move upward, which is strange because if we ignore this force, this part of the system will only go downward. So this feature needs special attention, and in particular the stiffness of this system can be arranged in a way to make this contribution identical to this contribution. In these cases, special cases, this force, axial force, will vanish, And so equilibrium of this system will be possible without any force here and therefore without any spring. These are exceptional cases, but in any case the presence of the Eshelby-like force gives effects which are unexpected, and in particular we will see from experiments that this point will move upward. So our intent now is to move to the lab and to confirm experimentally all the things I have shown you. We have derived theoretically all these effects, but now our interest is to show the presence of these effects in an experimental way. This is the experimental setup. The dead load is provided filling these two containers with water, and the load is measured through these two load cells, miniaturized. If we get rid of this container, we see the system with the penetrating blade. So this is the straight configuration, and when it buckles, it goes like this. What we measure here is the load and the vertical displacement using this non-contact transducer, and the acquisition is this one. The sliding sleeve is this piece and is realized with many rollers coated with Teflon, and the elastic spring is provided by this rigid bar hanged with two linear elastic springs. So our purpose is to load the system, measure displacement, and see how buckling evolves. After buckling, we will see that this rigid bar goes upward due to the Eshelby-like force.